So let's take a look at the magnetic moment of a rectangular coil. Here we've got a rectangle of 5.4 by 8.5 centimeters, and we have 25 turns of wire. It's carrying a current of 15 milliamps and has a magnetic field of magnitude 0.35 Tesla. And here's the things we want. What's the magnetic moment? What's the maximum magnitude of the magnetic torque on the coil? And what's the magnitude of the magnetic torque when the coil is at 60 degrees? So, initially, what's the magnitude of the magnetic moment? Well, we know that torque is mu cross B, and mu is the magnetic moment that we care about, which is I times A. So mu is N, that's the number of turns, times I times A. So mu becomes 25 times 15 times 10 to the minus 3 amps times 4.59 times 10 to the minus 3 meters squared. This is our 5.4 by 8.5 centimeters. And that will equal 1.72 times 10 to the minus 3 amp meters squared. So, our next part was to calculate the maximum magnitude of the magnetic torque. That is simply mu times B. We already calculated mu in the previous part. That's our 1.72 times 10 to the minus 3 amp meters squared. Let's multiply that by 0.35 Tesla. It's the definition of the Tesla that makes this work, because that tells us how much force essentially we'll get on a charged particle. And that will equal 6 times 10 to the minus 4 Newton meters in torque. The final part of discussing our rectangular coil was to find the magnitude of the magnetic coil here, magnetic torque, I apologize, for the coil at 60 degrees. Well, we already have most of this calculation done. Tau, our torque, is mu b sine theta. That's going to give us 6 times 10 to the minus 4 Newton meters times sine of 60, which will give us 5.22 times 10 to the minus 4 Newton meters. So that's our discussion of torque and how magnetism brings about torques. Where is this useful? Where do you see this the most? Well, if you look at a lab and you actually see a galvanometer moving, what that really is doing is passing a current through a coil. That coil is sitting between a permanent magnet, a north and south pole, in a constant B field. So every time you see one of those galvanometers give a reading, what's really going on is the current is passing through the coil, and then that's inducing a force in this galvanometer and physically moving this dial to a point on the scale. That's the conclusion of our discussion of magnetic fields.